address that I think is kind of neat. So I'm going to go off script a little bit, and we'll just do one more little theory thing. So someone asked, well, what happens if the cycles aren't disjoint? Right? I said they should be disjoint, have nothing in common. What happens if they have something in common? Very good question to ask. So, right, so these cycles have a number in common. Right? They've got this guy 2 that's repeated. So let's watch what happens when we apply this cycle to some numbers. 1, we'll plug in 1 here. This does nothing to 1. So it gets sent to 2. Right? So 1 goes here, nothing happens, 1 goes to 2. Okay? Now, 2, we plug it in, 2 goes to 3, no 3's here, so we get a 3. 3 goes to 2, goes to 1, so we get here. Okay, so there's the same symmetry written different ways. Now, let's watch what happens when we
smush it together.
Yeah, so it got smushed together, right? Let's watch what happens when we switch the order. Okay, so here, we'll do the same calculation. We plug in 1. 1 gets sent to 2. 2 gets sent to 3. Now we plug in 2. 2 gets sent to 1. 1 gets sent to 1. 3 gets sent to 2.
So it's counterclockwise.
Yeah, great. So we get these 2 rotations. But notice that these are not equal as functions, right? For this function, 1 goes to 2. For this function, 1 goes to 3. These guys are not equal. Yes?
How come you started this way instead of the normal left to right?
Oh, yeah, sorry. Just the habit. Yeah. Yes. Yeah. So I was thinking of this function applied to a number. You know, usually when you have functions, you write the variable over here. That's why I went that way. Multiply it the other way as well. So yes, so if the cycles are not disjoint, you get different answers based on different orders. They represent different symmetries. Yes?
But then if you just put them together, they're both rotational symmetries of if you just take the 2 cycles and put them together into a 1, 2, 3. They're both just rotations of 1, 2, 3.
Oh, but there's these brackets, right? So this guy actually, both of these actually represent reflections. Right, so this switches 2 numbers. So it's sort of a reflection. This is also a reflection. So when we take a product of 2 reflections, we get a rotation. The order matters.
So since you can make a cycle out of it, like this shape has a graphical representation, right?
Yeah.
So is that basically saying like you can reflect it, but it's not symmetrical? The result.
Right. So yeah, let's talk about what really is going on here. So this guy is this reflection, right? So this first term here. 2, 3 is this reflection. And then this term 1, 2 is this reflection. And it turns out the order that you reflect gives you a different symmetry. If you do blue then red, you get one symmetry. If you do red then blue, you get another. So we're gonna explore this more deeply with some hands-on stuff. Okay? So I want to take you a little bit further into the symmetry stuff with, oh yes, right, okay, good. With this crazy thing. What is this crazy thing?
It's a molecule.
Yeah, let's all say it together. Octomethylcysteine. Indeed.
Still says.
So this is a molecule. I found it online, and you can like spin it and rotate it and stuff. A lot of this symmetry stuff that we're talking about today with cycles and all this gets applied in chemistry to figure out the properties of molecules. Okay, so this is something chemists can synthesize this in their labs. It turns out it's very heavy because it's got a ton of carbon in it. But it's got a particular symmetry to it. And if we understand the symmetries of these molecules, we can understand something about how they react with other chemicals. So now that we've learned all about cycles and symmetries and stuff, I want to like get our hands dirty and actually do something with it. We don't have those models though. We've got these models. So as I was saying earlier about this process of abstraction, mathematicians can look at octamethylcysteine. They can look at this and they can see that it's kind of got this this square structure inside it. If you look at the pink nodes, there's squares of them, and that represents a cube or an octahedron. Yes.
Where's the pig?
Sorry. Sorry. Oh yeah. Sorry. It doesn't look pink to you. These guys. The kind of fleshy colored ones, maybe? I don't know.
That's good.
The whatever these guys are colored. Beige. Yeah, the beige ones. Anyway, there's 8 of them. They form the vertices of a cube. And the symmetries of the cube are the symmetries of this molecule. So mathematicians study objects like cubes and octahedra and discover the sort of fundamental building blocks of symmetry. And then when they run into a monster like this, they can recognize those symmetries. So if you've got any more meetings with chemists tomorrow, ask them about symmetries, because chemists love symmetry. Okay, so we've got these guys instead, sort of the simpler, more ideal versions of these things. So if you could get and sort of find your favorite people here, the people you work well with, okay? Rearrange.
Into groups of what? How many?
I don't know, man. I'm down to work with someone smart, though. Jeffrey, let's go. Jeffrey, wait, how many groups?
11 groups. How many people in a group? 5. No. Yes.